so much for being here on time. I would like to introduce Megan from GERSTEL. And as we mentioned earlier, we are the people who do the process, more on the textural properties, structure, but GERSTEL, Megan and Corey helping us to, and of course Dr. Jing helping us to understand more the chemistry and the flavors. And as you've seen, I've seen that the process, the ingredients, the conditions will affect the flavors, and hopefully with the technology they provide in GERSTEL, that we could understand more about those plant-based alternatives. So without further delay, I'll introduce Megan from GERSTEL.
Thank you. So for the next 30 minutes, I want to give a brief overview of who we are at GERSTEL, and then I want to give an introduction on sample extraction and introduction techniques. And then the last couple of slides, we're going to focus on sensory-directed analysis of 2 plant-based products that we've worked with. So just to give a general understanding of who we have in the room, I know we have a lot of food science majors in here. Have we all taken organic chemistry? Okay, great. So we know a good amount about functional groups and things of that nature. Has anybody taken analytical chemistry? Okay, so not so much. So a key thing that we're going to be discussing here is gas chromatography, mass spectrometry. Are we familiar with that instrument? Okay, I have some nods. That's great. All right, so we can get going here. So just a brief overview of who we are at GERSTEL. We are a family-owned company founded in 1967. We recently joined a group called Advanced Automation Technologies, so we are kind of adjacent level to Scalar, Promachrome. You may have heard of them, you may not have. But GERSTEL headquarters are located in Mulheim, Germany. We have several subsidiaries, one being located in the US, so I came from Baltimore, Maryland. That's where our main US subsidiary is. We also have locations in Switzerland, Japan, China, and Singapore, but we're really represented in numerous countries throughout the world. So what GERSTEL does is solve analytical challenges for sample prep, sample extraction, and introduction techniques. So believe it or not, this is by no means a comprehensive list of what we offer, but for purposes of today, we're going to go over on the back end what the olfactory detection port can do for us, as well as discuss some sample extraction and introduction techniques, specifically focusing on thermal desorption, or what we refer to as TD or TDU. So at GERSTEL, like I mentioned, we automate sample preparation, extraction, and introduction, and we can do so on GC, GCMS, LC, LCMS systems, or on offline workstations. So how many of us have built a calibration curve? We prepared standards, we do that all manually with pipettes, right? Imagine if you could automate that on a rail. You can just press a button, go, walk away, you're prepping all your standards. For purposes of today, we won't get into LC, LCMS, but we can also automate extraction processes on a GC, GCMS system to automate that extraction and then ultimately identify important flavor compounds in plant-based products. I'm not going to focus on automation today. These are several reasons why you would want to automate. The big idea here is just that we are freeing up your time. You can spend it more doing data analysis or perhaps research. The instrument can essentially run 24/7, okay? So the first thing I want to discuss is sample extraction and introduction. With the GCMS instrumentation, we're all pretty familiar with liquid injection, right? It's probably the first technique that we learned with GC. There's also things like static headspace, solid phase microextraction, and then what we're really going to be focusing on today is some thermal desorption techniques, okay? Before we discuss each of those, it's really important to introduce the inlet into the equation. So are we all familiar with what the inlet does on a GCMS instrument? I'm getting some no's. So with GC, we need to volatilize our sample. The inlet is the main component that's going to do that for us to ensure that compounds are introduced in the gas phase. So GERSTEL offers a CIS inlet, which stands for Cooled Injection System, and it's a programmable temperature vaporizer style inlet that allows for precise temperature control for sample introduction. It differs in terms of splitless style inlets, what you typically see with Agilent or thermo instruments. But the main thing today is that we want to focus on the fact that it can be employed as a cold trap, which is really, really important for thermal desorption techniques. All right, so before we discuss thermal desorption, I want to take the time to talk about liquid, static headspace, and SPME. They're more traditional means of extracting and introducing sample extracts, but in terms of plant-based foods, they don't give us enough sensitivity to identify sensory active compounds, things that contribute to flavor. So liquid injection is very easy to implement with GCMS. Perhaps you did a liquid-liquid extraction, or you're diluting your sample of interest. You're directly injecting it into the GC, it volatilizes, you get your data. But with this technique, you might be introducing a very high amount of your sample matrix, whether that's your solvent or an oil, so there's no pre-concentration of those analytes of interest. And because of that, you're going to get relatively high detection limits. So if you have any trace level compounds, which is very common in flavor work, you won't be able to see them. Static headspace, on the other hand, is able to effectively eliminate your matrix from the equation. So your sample is going to incubate in an isothermal incubator, allow for analytes to diffuse out of your sample into the headspace, and then a static headspace syringe will pull up an aliquot of sample and inject it into the GC. Due to the nature of the equilibrium process, it does do a great job of extracting more volatile components, but it struggles with the semi-volatiles, and because of that, we also see relatively high detection limits with static headspace as well. So not one of the techniques that we'd recommend for plant-based studies. And then a more traditional approach with food studies is the utilization of solid phase microextraction, or what you might hear me call it SPME. And so it's also an equilibrium-based technique, but rather than pulling up an aliquot of sample, we have this fiber that's coated in some sort of polymeric phase, which allows our analytes to have additional affinity for it, which means that we can enhance our extraction efficiency by increasing selectivity. Okay? SPME fibers can be used in the headspace of the sample. They can also be immersed in a liquid sample. So we definitely see improved detection limits with this technique compared to static headspace and liquid injection. But where SPME falters is the fact that these fibers used to extract samples of interest are very fragile. You're likely going to break them before you can even reuse them down the road. And they also suffer with capacity, which is the amount of sorbent available to your sample of interest to effectively extract the widest range of compounds in your sample, specifically flavor compounds. So that brings us to thermal desorption. And what thermal desorption essentially is a sample introduction technique for gas chromatography mass spectrometry. So this is our thermal desorption unit here. It sits right on top of the CIS inlet, which I mentioned to you before. And essentially, a thermal desorption unit is going to have some sort of tube full of solid sample, or perhaps a sorbent material. It can also be a liquid sample. And what we're going to do is expose our sample to high heat and high flow to release analytes of interest from the material and for them to be trapped in the CIS inlet before GCMS introduction. So this high heat and high flow eliminates an equilibrium-based process, meaning that as flow redirects analytes onto a trap, we are constantly reestablishing equilibrium, which further drives analytes out of the sample and into the headspace. So it's a continuous process. Yes, Bilal?
What's the form of the sample that can go in there?
Yes.
Solid, liquid, can I have a whole piece of meat?
Yes, you could. Yep, so these tubes here, this is displaying a solid sample in an empty fritted tube. This one here is showing a sorbent material. So we technically use these for dynamic headspace setups, which we'll talk about in a couple of slides, or for air sampling, if you all have heard anything about that. We also have separate extraction devices, which Dr. Zhao has been using for her work, called twister and thin film SPME membranes. We're going to touch on those as well. Or you can place a liquid sample in a microvial to be desorbed as well. So really, we can touch on all sorts of sample types with this.
No drying required.
No.
The whole sample
No.
as it is.
No
The
sample
native
prep,
state.
just insert it directly.
Yeah, so theoretically it's doable, but in practice we don't do that because for meat product, thermal desorption unit to keep the sample, so it actually changes the flavor response. So we have the demo later in the afternoon that show you the temperature effect. If we're trying to control the temperature, we sometimes do cold extraction overnight to help concentrate the molecules. If we keep the temperature low, UTDU, with a short period of time, with it generating alcohols and soy acids.
Thanks, Jane. All right. So thermodesorption is going to be a two-step process, and we're showing that in this graphic here. So we talked about the sample types that we can utilize in the TDU. It's going to be placed directly in the thermal desorption unit, and we're going to expose it to high heat and high flow. During that time, analytes are going to be refocused in a zone of smaller dimensions, a Kohler zone of smaller dimensions, aka the CIS inlet. And then after the desorption period, our CIS inlet is able to increase in temperature to transfer our analytes of interest to the GC column. Now this trapping step is really, really important because the TDU is much larger than the CIS, and so we want to trap our analytes into a cooler zone so that the materials can condense, and then upon introduction to the GC column and detection, we get nice sharp peaks. Without this step, we're going to get ugly blobs, and it's not going to really give us that interpretable data. So that brings us to thermal desorption techniques. Thermal desorption is essentially an umbrella term that we utilize, but there are a variety of approaches that we can take here. So we mentioned twister, we mentioned thin film solid phase microextraction, we have direct thermal extraction, so Bilal, that's where we insert solid samples directly in a tube or a liquid sample directly in a tube. We have air and field sampling, and then we have dynamic headspace. Yeah, Corey.
And I have examples.
Oh, beautiful.
Our twister bars here, and then we have our thin film spoomy fibers. I'm just going to pass these around.
Thanks,
So
Corey.
you guys can take a closer look at some of the techniques.
All right. Yes, so for purposes of today, as we focus on plant-based foods, we're going to hint on twister and thin film SPME, as well as dynamic headspace methodology. So as we're passing those around, you'll see a twister stir bar in one of those vials. It's very, very tiny, looks kind of like a Tic Tac, but please don't eat it. It's going to be a metal stir bar that's encapsulated in glass with a polydimethylsiloxane coating on the outside, or what we call PDMS. So the extraction kind of works the same as a liquid-liquid extraction. Have we all worked with liquid-liquid extractions with like separatory funnels? Okay, same sort of idea here where our matrix is one liquid and then the PDMS functions as a low amount of immobilized solvent. So whether our analytes have a higher or lower affinity depends on what we can extract. Extraction is based on sorption. So what affinity do our analytes have for the PDMS phase? PDMS is nonpolar in nature, so the twister stir bar does an excellent job of extracting nonpolar analytes of interest, or those with higher log octanol water partition coefficients. Okay? These twister devices can be used immersively in the headspace above your sample, or even direct contact sampling. And we really like to utilize these in aqueous or humid environments because PDMS is fully inert and it doesn't retain water. All right? After our extraction, this twister device can be placed in an empty TDU tube and desorbed via GCMS analysis. Yes?
Yeah, I was very interested. I couldn't hold up anymore when you said partition coefficient.
Yes.
So is this driven by the classical thermodynamic partitioning?
Yes and no. Yeah, it's more so focused on polarity, non-polarity. Twister does a great job of extracting nonpolar analytes.
But that's in fact also the partition coefficients reflect polarity and non-polarity.
Yes. Yeah.
So would this correlate with, let's say, partition coefficients of these volatiles in your PDMS or not?
I'm not sure I understand the question.
So because it's based on partitioning, you get very quantitative.
Mm-hmm.
So is this a very quantitative way to analyze these compounds?
Mm-hmm.
So you can render it very quantitative.
Mm-hmm.
Absorption techniques usually is a little bit more tricky.
Yes.
Yeah, okay, so it's probably partitioning involved.
Mm-hmm.
Yes, thank you.
All right. So after our extraction, we place the twister device directly into an empty tube, and then we can complete desorption. Compared to solid phase microextraction, these extraction devices can get down to extremely low detection limits, down to parts per quadrillion, which make them great candidates for plant-based studies when we're extracting extremely low concentration and low odor threshold compounds. Ooh, there we go. In a similar way, we have thin film solid phase microextraction devices. So that's going to be that carbon mesh membrane that we passed around, and it kind of looks like a flattened SPME fiber. So what we're doing here is offering additional surface area and phase volume available, so more capacity so that we can extract analytes of interest. Now, unlike the twister, it's not just composed of polydimethylsiloxane, but we have phases available in divinylbenzene as well as hydrophilic lipophilic balanced particles, or what we refer to as HLB. These are more polar sorbent materials, which means that we can extract not only our nonpolar analytes, but our more polar ones as well. So really the widest range of VOCs available in our sample, allowing us a more comprehensive means of looking at data. We're comparing the phase volumes of SPME and thin film SPME here just to show you the difference between the two. These devices can also be used in the headspace or immersively, so really diversifying your extraction workflow. They're reusable just like SPME fibers, and they can be suspended with these special holders and sample vials. Now you might be asking yourself, okay, well you talked about twister and you talked about thin film SPME, can I use them together? And the answer to that is yes. So we're just showing the twister thin film SPME extraction workflow here. Again, with a liquid sample, we're gonna immerse both directly in the solution. With a solid sample, it'll be placed in the headspace above it. During this time, the devices sit, they either stir or agitate for a period of time. Analytes partition out of our sample and then adsorb onto or into the extraction devices. If we did immersive, we'll rinse off the extraction devices to get rid of any non-specific attachments. So if we're working, say, with a beverage, it would get rid of sugars that are on the coatings. And then both devices can be placed in an empty thermal desorption tube, exposed to high heat and high flow, and ultimately GCMS analysis. So if you're more of a visual learner, I talked a little bit about phase volume. That's really just the amount of sorbent available to you to promote your extraction efficiency. When you use twister and thin film SPME combined, you get a total of 33 microliters of phase volume. When you look at a standard SPME fiber, we're only working with 0.6 microliters of phase volume. So the amount of capacity that you have available is wildly different. This is about 55 times greater, meaning that we can really achieve extremely low detection limits for our plant-based studies. So what we're showing here is an example of the extraction of hydrated protein powders using both headspace SPME and immersive twister thin film SPME. And really what we want to point out here in the GC chromatograms is not only are we seeing more peak signal intensity with the twister thin film SPME extraction, but we're also able to extract some compounds that are later eluters. That's because it was used immersively and also because twister thin film SPME has that higher capacity to extract these compounds. So this is really a great candidate, like I mentioned, for plant-based studies. We're seeing things like vanillin that smells like vanilla. We see things like some lactones that offer creamy and kind of peachy-like aromas. We also get some fatty acids here that might contribute to sweaty aromas. Okay, so we really like utilizing thermal desorption techniques for plant-based studies. The last extraction technique that I want to talk to you all about is dynamic headspace. Dynamic headspace is a completely automated means of sample extraction. It's pictured here on our rail in this red box. Ignore this one right here. And it offers little to no analyte discrimination, ensuring that we have a comprehensive VOC profile of our samples of interest. So the way dynamic headspace works is that we will have a sample vial with a liquid or solid sample that's inserted directly inside the DHS. It's going to be incubated, and then the DHS has this dual needle system where a purge flow is going to come through the sample vial, sweep the headspace, and then redirect analytes of interest onto a sorbent material. Sorbents can be something like 10xTA, which is a porous polymer. They can be something like carbopack materials, which are a little more adsorptive in strength. After that, if we have any sort of moisture, we can eliminate it with a dry purge step. And then that tube is going to be directly inserted into the thermal desorption unit for GCMS analysis. So another very sensitive extraction technique where you can achieve extremely low detection limits because we're not relying on an equilibrium-based process. One cool feature of the DHS is the ability to analyze large sample sizes. So perhaps you wanted to insert a whole cheeseburger in there or a whole plant-based chicken nugget. We offer vessel sizes up to 1 liter in volume, so you can really optimize your workflow and work with a variety of sample types. We often have customers utilizing this because they're afraid that their sample isn't homogeneous, and so if they take a cutting of it, maybe it's not going to be representative of the entire thing. So that was a lot about extraction techniques. Do we have any questions about that before I jump into sensory? Yes, Bilal.
I wake up in the morning, I bring my meat analogs, I want to decide which extraction method. I'm so lost now. Which one will give me a decision to move forward to choose process A or B or C, or I buy flavor from CJ Bio, or maybe I buy from another company? How do I make a decision? Because now I have so many extraction methods, I have samples, so I know water soluble, fat soluble, but I'm so confused now. So you can help us.
Absolutely. So I introduced liquid, static headspace, and solid phase microextraction just because they're more traditional, more common in the literature. I would say don't use those. Use any thermal desorption based technique. If you're working with something like hydrated pea protein powders, I would say go the twister thin film SPME route because it selectively eliminates water from the matrix, allowing you to extract only the VOCs of interest from the pea protein powder. If you're working with a meat analog of interest, my recommendation would be to utilize dynamic headspace. It's really great for solid samples. I already mentioned that no analyte discrimination is typically seen with this, and you can really adjust temperature, or you can work in cooler zones and optimize your extraction that way. So to answer your question, either dynamic headspace or twister thin film SPME, our applications lab would give you a recommendation based on your sample type.
I'll take dynamic headspace.
Okay.
If I do a dose study, will I be able to capture that? Which means I introduce the flavors. I was talking with Christine this morning. So some of the flavors may be recommended 0.5%. If I added 1%, 1.5%, with that technique, I will be able to capture that intensity?
Yes, you can.
And
you
link it with my sensory evaluation.
Exactly. So one thing to mention with that, when we think about sensory work, it's kind of black magic, but sometimes we're able to perceive something via the human nose that the instrument is not able to detect. So you talk about change in flavors that you add, we could probably perceive that via the nose. That doesn't necessarily mean that the instrument is able to pick it up. Okay, so the extraction technique can help us extract those flavor compounds of interest, and we might be able to perceive them at the ODP, which we're going to talk about in a minute here. But we need that correlation with data to actually be able to determine what those compounds are. That'll make more sense in a couple of slides. Go for it.
Is it preferred to use internal or external standard?
So it's preferred to use...
And if you can just highlight to my student what the difference between internal and external standard.
Yes.
I know they make difference.
Yes.
You do the intensity detection?
Yes, they do. So we usually recommend getting matrix match standards. With these thermal desorption techniques, we deem them exhaustive, which means we fully extracted our compounds of interest. So in that case, external standard calibration would be a great technique to use. That means that you prepare standards of no concentration and you plot their response against their concentration. You ultimately should get a linear curve to be able to determine the concentration of flavors in an unknown sample. Along with external calibration, you can also implement internal standards. And these internal standards sometimes are deuterated, so you might have D8 whatever, deuterium labeled isotopes, and they are supposed to have a similar response to your analytes of interest to account for any instrument fluctuations, things like that. They can also be plotted in an external standard calibration curve. If you are struggling with getting matrix match standards, you can also do what's called a method of standard additions, whereby you add a known amount of standard to your sample, and you increase the amount of standard that you add to that sample, and you again can plot a linear curve. But in order to determine the concentration that's actually in your sample, it's going to be where the curve crosses the x-axis intercept. Okay, so that's going to be the absolute value of that point there, and that's going to determine the concentration of which exists in your sample. I know that that was a lengthy answer, but hopefully that made sense. I had some nods with some of you. Okay? All right, So this is my favorite thing to talk about in terms of work that we do with the GC, and it's sensory-directed analysis. So what is sensory-directed analysis? You might hear me refer to it as SDA because we love our acronyms around here. But it's essentially a method that's going to utilize the separation and detection power of GCMS with our human nose, so the olfactory, the sensory component. Now, we spent a lot of time discussing extraction techniques because it's a key step of the sensory-directed analysis process. It's a 7-step workflow and with the ultimate goal of determining a sensory active compound. So what is a sensory active compound? It's specifically a compound that's going to be present at a concentration above its odor detection threshold. Okay? If you have an odor detection threshold of one compound that is 1 ppb, 1 part per billion, and it's at a concentration of less than 1 ppb, you won't be able to perceive it with the nose. If it exists, say, at 1 ppm, you should now be able to smell it at your nose, and that's sensory active, okay? The perceived odor of a material, of a plant-based product, is going to be composed of numerous sensory active compounds. It's never just going to be one, it's going to be multiple. But a common misconception when we look at GCMS data is that each peak in a chromatogram is going to correlate with a sensory active compound of interest. And that's essentially not true. So that's why we need to employ some sensory evaluation along with GCMS data to see where things correlate. So how do we do that? GERSTEL offers a detection port called the ODP, or olfactory detection port. It essentially functions as a detector after the GC column, and it's pictured on the right-hand side of our instrument here. So if I zoom into it, think about your GC column. It'll then go to a splitter so that we can split our compounds of interest to not only the mass spec, but also the ODP. And to do so, we have this heated transfer line, which is going to have a capillary that's heated up to direct analytes this way. We also have a heated mixing chamber where our analytes of interest are going to mix with some water vapors so that while we are employed as the detector, we sit at the nose cone of the ODP, and that additional humidification is used to make sure our noses don't dry out, okay? So ultimately here, we are linking GCMS with olfactory data. In an ideal world, something sensed at the ODP will also be detected via the mass spec. So this graphic is kind of just a cutaway view of what we're working with here. We have our CIS inlet, the GC column, the splitter, and then 2 capillaries that are going to lead to both of our detectors. So I'm going to play this graphic here. Our sample extract is introduced. GC column is utilized to separate important analytes of interest. And in an ideal world, like I mentioned, something perceived at the ODP will be detected at the mass spec. So if I'm sitting there and I sniff something like lavender, and when I get a peak for it that correlates, the compound identified is linalool. And because I'm familiar with this work and I know about sensory activity, I can say, you know what, that compound is linalool. Linalool does smell like lavender or floral, okay? With plant-based work, chromatograms are not this pretty. This is a very pretty chromatogram. Sometimes we get coelution. Do we know what that is? Okay, so that's where peaks kind of overlap with each other and we can't get a good identification of compounds because they're eluting together. Sometimes we're able to sniff something at the ODP, but we don't get a peak. So that happens because our noses are actually far more sensitive than any detector out there. So we are a very powerful tool, and the sensory aspect of it is really going to be a driving factor for sensory-directed analysis. So that leads us to the 2 examples that I want to talk about to you all today. We were investigating plant-based versus real tuna fish. In doing so, we purchased 2 plant-based tuna fish products from a local store, as well as some real canned tuna fish. And what we wanted to do here was just compare aroma profile differences between the 2. So we're going to lead with the sensory-directed analysis process. I said it was 7 steps. First step here is to determine our aroma descriptors. We've all eaten tuna fish before, right? Or at least smelled it. I think we can all agree that fishy, brothy, meaty is a good way to describe it initially, yes? The first plant-based tuna fish that we evaluated was described more so as beany, vegetal. The second one more so grainy, vegetal, and seaweed-like in nature. Okay? That brings us, did somebody have a question? Okay. That brings us to the second step of the SDA process, which is to extract our analytes of interest. Bilal said, I introduced a lot of sample extraction techniques. Which ones do I choose? DHS is really the key extraction technique that we like to use for this type of analysis. So these are our parameters here. We can talk in more detail after if you'd like. It gets into the nitty-gritty of things, so I'm just going to continue. Before we introduce our sorbent material at the TDU, we like to perform something called an extraction verification. So, okay, I perform my dynamic headspace extraction. How do I know that it fully extracted those volatile organic compounds that represent that of the sample, of which identified the aromas that were in the initial sensory evaluation, right? So we're going to be working with this, Jing and I, this afternoon with the TE. So I'm left with the sorbent-filled tube that has my analytes trapped onto it, right? If I insert that tube into this heater block here for a couple of minutes, those analytes are going to desorb off the material after, say, 3 to 5 minutes. I'm then going to apply gas flow through this system, and I'm going to sniff the total odor profile that comes off of it. In doing so, I can confirm or deny whether my extraction technique was successful. We did this for the plant-based tuna fish samples as well as the real tuna fish, and they were extremely representative of the original sample that we evaluated in the sensory panel. So we were able to say, great, this was a successful extraction technique. Let's re-extract, introduce it to the GCMS via thermal desorption. These were our parameters that we followed. And then we end up with some data that we can analyze. So, if you've never seen a GC chromatogram before, it's essentially just response plotted against retention time. Each analyte of interest is going to have a different retention time depending on how it interacts with the GC column. So that's going to be the red trace that you see here, real tuna on top, plant-based 1 and 2 in the middle and bottom. We also have these yellow blocks here, which is going to represent the odor regions identified at the ODP. So it's a little hard to see, but the grade words on the side are the aroma descriptors that we identified at the ODP. But what we're really pointing out here is what's blocked out in blue. And these specifically are the aroma descriptors that we described in the initial sensory panel evaluation. So we want to investigate these in more detail. Now, I talked about coelution, right? So that's where 2 peaks are kind of unresolved. We want to be able to get efficient separation to be able to identify them. I'm not going to get into the nitty-gritty of what a 1D, 2D GCOMS is, but essentially it employs 2 columns of dissimilar phase so that you can get enhanced separation on a column, say, that separates via boiling point. The second one would separate via polarity. Okay, so doing a little bit different of chemistry here. So, with the real tuna fish sample, around 2.4 minutes, we have coelution. We have one region that was described as sulfur and garbagey, but we also have this fishy aroma that we identified in the initial sensory panel evaluation. Because they're coeluting, we can't get a good identification on this peak. So we took it from a column that is a dB5MS, that's really just a boiling point separation column. We then introduced that region onto a column that was wax phase, so now it's separating via polarity. And now we have separation of that odor and the compound of interest, and we were able to identify it as trimethylamine. Okay? Yes, Bilal?
I'm so sorry, I did not afford to go to Harper or Stanford and just food scientists who, went to Pomona or teach in Pomona. I will not be able to do the GCMS analysis, but what is your recommendation for me to make a decision? Like, I'm a food scientist, I'm developing a formulation, again, to make a decision to buy a certain ingredient, or I work for a company that sells ingredients that we want to convince our client this is something applicable or something that's useful to improve the flavors in their products. What should I focus on? What should I learn? how do I distinguish between all these peaks and profiles without going to really, we teach chemistry, but really on the very light side. We learn it, but I want to be in a position that I can make a decision based on this data.
So based on this data, I would say, really for you all, I understand that GC data is a bit complex if you're not an analytical chemist at heart, but really what's going to drive it for you and as a consumer is the sensory data, okay? So especially when comparing real products with plant-based products, the fishy odor was detected in the real tuna fish, right? But what we're going to see is that it was not detected in the plant-based products. As we very well know, tuna is a fish. It's a key component of that real meat flavor. So how can we formulate that into a plant-based product to ensure that flavor matches that of the original sample? So this is, go ahead, Corey.
Well, I just going to expand on that question too. GERSTEL, whenever we enter a consultation with a company, we aren't just working with your standard analytical chemist, which Megan is an amazing analytical chemist, that her scope is beyond just plant-based food work. She also has a background in forensics. That's incredible. So that's just one scope of my process with a company. I also work with flavor chemists, and flavor chemists are not sitting at the instrument running the data. They're cohesively working as a team with an analytical chemist that runs this data, and maybe they evaluate that data. Maybe they do some flavor duplication type work. They take that data and try to create a duplicate flavor out of it, or aroma if you're in perfumery. That's how this kind of instrument is used at the company level in a manufacturing setting.
Yeah. Does that make sense? So in plant-based number 1, we also saw coelution. Upon introducing it to a different column, we got coelution again, which isn't great. This does happen sometimes, especially when two compounds have very similar chemistry. But this is to note the fact that we want the nose to be our guide. And so not only do we have an identify step with the sensory-directed analysis process, we also have a confirmation step. So we saw the same sort of coelution with plant-based 2 as well. What the confirmation step is utilized for is to take known standards of potential compounds that we've identified in each of our samples and compare not only retention time, mass spectra, that's more on the chemistry side, but also compare their odors, okay? So we obtained a standard of trimethylamine, we evaluated it via DHS, determined that trimethylamine indeed smells fishy, so yes, that is the odor that we identified definitively in the real tuna fish sample. With plant-based tuna fish number 1, we had coelution of allyl methyl sulfide and 2-ethylfuran, okay? When we evaluated both of those standards at the ODP after DHS introduction, 2-ethylfuran wasn't odor active. So that's a good indication that allyl methyl sulfide was actually the compound that we identified. So again, this is where sensory is going to drive compound identification. That's what's contributing to the aroma of our sample. Unfortunately, with plant-based tuna fish number 2, we didn't have a standard for 2-methylbutanol. Sometimes they discontinue them depending on the vendor that you're working with. So we weren't able to confirm retention time and odor, but we did confirm it for 3-methylbutanol to identify those compounds. So what we've learned from this study is that we're able to identify sensory active compounds in plant-based tuna fish and compare them to real tuna fish. So we know that real tuna was the only sample that had trimethylamine in the GC chromatogram, right? And that's what contributed to the fishy odor that we're also familiar with a real tuna fish product. But it was indeed missing from the plant-based product. So again, affecting flavor. We talked about 1D2D-GC-OMS. I'm gonna skip that for now, just to point out that it's a useful tool for resolving areas where coelution may occur, but I think for all of us, it's a bit in too much detail. All right, so the last example I want to walk through is a collaboration that we completed with CalSec Incorporated. Are we all familiar with them? They're located in Kalamazoo, Michigan. So they focus on flavor, formulation, and ingredients for plant-based food preservation. They also do it with beverages. And so they wanted to work with us by investigating the use of a rosemary extract, which is an antioxidant additive, to see if it preserves plant-based meat alternative products, whether or not we can elongate the freshness of it. So they shipped control patties to us as well as these rosemary extract treated patties to us. And we just were monitoring storage periods for 0, 7, 14, 21, and 21 days. Okay? So again, we're at the first step of the sensory-directed analysis process. What are our aroma descriptors of each of those patties on days 0, 7, 14, and 21, and 28? As you can see here, day 28 did not have any data associated with it. That's because we did not conduct a sensory panel on it. CalSec deemed that at day 28, the microbial level was a little too high for the patties, so they said, you probably shouldn't eat it. So that's why you don't see any data there. Day 0, they were described as grainy, oaty, green peas, beany, typical of your plant-based products. But then after day 7, 14, and 21, in the control, we get some of these, what we call oxidized off notes. So oxidation can occur as a result of samples spent in storage. And so oxidation can be described as nutty, oxidized, even paint or oily in quality, undesirable things that we want to eat. In the rosemary extract treated patties, these aroma descriptors were only described as slight, meaning that the rosemary extract is doing something to prevent oxidation. Okay? We extracted via DHS. We confirmed that our extraction was successful using the thermal extractor. We then introduced our sample extract onto the system, and then we ended up with this GC chromatogram. Okay? When we overlay the sensory data with the GC chromatogram, you can see that there are several regions of interest where we identified something at the ODP that may or may not have correlated with the chemical data that we obtained via GCMS. As you can see on day 0, I'm not blocking out anything with the blue rectangle here, and that's because we identified no off odors in either the control or the rosemary extract treated patties. But when we get out to day 28, you see several regions that are blocked off. And these regions were described as fried, oily, nutty, which are oxidation off odors that we don't want in our products. You can see in the control, we identified 7. In the rosemary extract, only 4. We did get some identification of these compounds. They are aldehydes and pyrazines. Oftentimes, aldehydes are common oxidation byproducts. Pyrazines are a result of Maillard reactions. Maillard reactions are often favorable. They contribute to very roasted, nutty aromas, but they can also be non-favorable in this setting and form during storage. We even got some identification of multiple compounds, but in the control, we also detected areas that had an odor correlated with it, but I wasn't able to identify a peak. So again, we're leading with our nose here. Sometimes we're able to perceive sensory active compounds at the ODP where the instrument's not able to pick it up. So that's where the ODP is really that driving factor. Another thing to point out here is that one particular pyrazine that we were investigating for the control, its peak area response actually increased throughout the storage period for the control patty. In the treated patty, it remained pretty stagnant. So that's saying that the rosemary extract was doing its role in preserving freshness. So back to the idea that we have peaks, or lack of peaks, that can't correlate with odors. What can we do to increase what we call analyte mass on column to actually produce a peak so we can identify what compound correlates with an odor? GERSTEL offers something called TD multi-desorption mode, where you can stack multiple dynamic headspace extractions and introduce them in one go. So for extraction here, that means that you'll get 4 times the analyte mass on column compared to a single one. So we had some regions. Over here you can see that we had one single extraction where we didn't see a peak, but we described an odor as slight paint and oxidized. When we introduce 3 times the amount via 3 extractions, we now get this blip here. So we're able to correlate an odor with a detectable and identifiable peak. Another region over here didn't correlate with an odor, But we did get this small hump and identified 2 additional pyrazines. And we believe that these may have contributed to what we call synergistic effects. Do we know what synergistic effects are? Yes, some of us. Do we need a refresher? Does anybody want to share what it is? Okay, so synergistic effects is essentially when 2 compounds work together to produce an aroma. With GC, we're separating via the GC column, so we're not able to sniff them because they're separate from each other. They're not working together, okay? So that's why we don't have any sort of odor associated with it. So that leads us to our confirmation step. Let's confirm that these compounds match retention time, mass spectra, as well as their odor. We were able to run standards for every compound identified except one. Unfortunately, with this compound, we again weren't able to obtain it from our vendor of choice, so we had to opt not to run it. For the aldehydes, the ones that contribute to oxidation, we were able to confirm odor and retention time mass spectra for all except benzene acetaldehyde. So in the sample, we determined that this region was described as nutty and burnt, and while it correlated with benzene acetaldehyde, when I ran the standard, it was described as honey and floral. So we can't deem that as an acceptable compound for identification. This means that we'd have to do some additional work. Perhaps the odor is extremely low threshold, exists at extremely low concentrations. So we need to do something else to increase that peak signal intensity to correlate the peak with an odor. Same idea with the pyrazines, ran known standards, compared it to odor regions of interest for our sample, and we were able to confirm every single one of them. Trimethylpyrazine was one of those compounds that may have contributed to synergistic effects. Without being eluded with another compound of interest, we don't get any sort of odor with it, okay? So in this study that we performed with CalSec, we determined that aldehydes and pyrazines were the primary off odors in the plant-based meat patties. We also know that longer storage periods resulted in an increased production of these compounds that were responsible for the off odors. But more importantly, we know that when we formulate antioxidant additives such as a rosemary extract, this is going to prolong our shelf life. And we use the ODP to confirm that. Some takeaways for you all is knowing that this GERSTEL sensory-directed analysis methodology is really the only means of definitively identifying sensory active compounds and being able to correlate them with our nose. We talked about odor thresholds, how they can be a challenge. Sometimes we're able to perceive compounds via our nose, but we can't detect them. So that's why we say, let your nose be your guide. The olfactory detection port and you as an analyst and as a detector are extremely, extremely powerful. Okay? I know that was a lot. Do we have any questions?
Thank you so much, Megan. Well, a bit behind, yes, behind, but we will have the break. The food is here, but before we jump into the food, we have Dr. Jintao. She has an hour, but hopefully she make it like 50 minutes. And we can continue the questions with Megan. I know I have a lot of questions for Megan. Understanding chemistry is not easy. I feel like it's challenging, but I think that's the most difficult part, to understand flavor chemistry, to work with flavors and understand the effects of the process on those flavors, how you retain them or lose them, or how the consumer experience. I will say simply, if I understand that, I would be in industry making triple what I'm making as a professor. But